right, today's topic of discussion should be short, but is an important prerequisite for many other algorithms and techniques in quantum computing. For example, Shor's algorithm, Grover's algorithm, Simon's algorithm, Bernstein-Vazirani, I'm pretty sure all utilize, at least in some form, the phenomenon of phase kickback. And so before discussing any of those algorithms, it's important to have an understanding of exactly what this is. And so that this, as I said, won't be long. It's a relatively straightforward concept. It's just sometimes not the most intuitive. So consider an example where we have some qubit settings like this, some wave functions, arbitrary states going in, arbitrary states down here, and then we have some controlled operation. What phase kickback state says that even if this is we understand what controlled operations are. So if this is for every, if we're assuming this is one qubit, every time this is in a one state, right, it has some effect down here, whatever the unitary is down here. What this tells us is that we can convert effectively global phases into local phases that have effects on the entire system. So what this is saying is that this outcome can be some operation. I don't want to use u here, but I'll maybe use some function of u, maybe eigenvalue of u is a common example that we'll see. I'll just make it v, I guess, v of v. So what this is saying is that in this operation, even though it's controlled, right, in our sort of intuition and classical understanding would tell us, okay, if we think a controlled statement, right, is saying if 0 do nothing, if 1 do u, right, this is our sort of understanding of what a control is. This doesn't make any sense, right? How is it affecting this qubit? That doesn't, right? Intuitively, at least for me, when learning about this, that doesn't make a lot of sense. So let's actually start with a concrete example. Let's suppose we have our qubit here and our qubit here. Let's compose a simple circuit where we apply a Hadamard gate over here, X gate right here, and then we do a controlled, and this is going to be a Z gate. So let's look at the wave function of the entire system at each of these points. So right here we have 0, where left will be the top qubit, 0, 0. All right, now let's look right here. We put the first one into a superposition. I'm just going to be dropping all the probabilities. It's irrelevant for this discussion, or for this example, because it's all the same. So we put it into our superposition here, and we have flipped this qubit right here. So now this can also be written as 0, 1, plus 1, 1, right? This is a factorable state, so it's not entangled. So now let's look at this. So we can apply the CZ gate onto this. Well, we know what CZ does. It applies the Z gate to the target if the control is 1, right? So that's our algorithmic understanding we just established. Okay, so is the control 1 here? No, it's 0. So clearly we are left with 0, 1. All right, let's look over here. Is the control 1? Absolutely. So this becomes, it flips the phase of this. The phase is -1. So we have -1, 1. So we took our control and we, went through the if-thens and we got this state. Well, now let's separate this state. We can just factor out the 1, right? This is pretty trivial. In both cases, we can factor this out, so we'll get 0 minus 1, 1. Now you might be looking at this and say, hey, wait a second. This operation that intuitively says, in some sort of classical sense, says we're using this top qubit to determine whether we should do something to the bottom qubit, ended up doing nothing to the bottom qubit and changed the top qubit. This had, right? So right here, if we consider, for now, let's just use these two. So this is here and this is here, right? This resulted in this effect, right? This would have been, if we did this process on the top qubit, this is exactly equivalent to 0 H Z, and then down here is, we can put the X or not, it doesn't matter. This is the exact same circuit in effect, because this operation just impacted this top qubit. And so this is the fun phenomenon of phase kickback, because think about if we sort of applied it down here, we're converting this information and we're making it local to this system. And so we can see how this is a very non-classical sort of understanding. Not that this can't be recreated in some sort of classical physics, just that in our maybe traditional understanding of algorithms and circuits and such, this doesn't make as much intuitive sense. But we can see that this is an important phenomenon. I'll just highlight two potential examples. One, just worth noting that this could be anything. This could be a T-gate, any unitary matrix, right, could work there. It's not a particularly, it's not important what that is. And if we want to go through the actual matrix multiplication, we know that the Z-gate, you can look it up or just trust me, is the following gate with this on the diagonal. Our qubit state, remember, was in the 0, 1 state and the 1, 1 state. So we have 1 over square root of 2, 1 over square root of 2, 0, 0. And so this clearly is 0, 1 over square root of 2, 0, negative 1 over square root of 2. So for those of you who wanted the matrix of this done out. So now we can see this is possible for any unitary matrix, but we can get a little hint as to when this is going to be important. Let's consider an example where we have some, that's not what I want, we have some unitary operations here, where this time this is going to be in the plus state, and this is going to be in the minus state, which just remember, this corresponds to 0 plus minus 1 over square root of 2. And now let's suppose we have some controlled operation that does the following. It takes this state in and it does, we can call this Y, I guess, but it's going to do the modular or XOR of some binary function. So we'll just call this Y. So this is Y and this is X, and it's going to be some binary function of X. So for example, if X is 1, maybe it'll be 1. If X is 0, it'll be 0. That would be the identity function, right? We can see that this can impact. We can say, okay, this is what the unitary does, right? So this is the effect of the unitary. But now let's consider a sort of trivial example of this, where, so remember, X is 0 plus 1. I'm going to ignore once again the the probabilities or the amplitudes. And then, all right, let's suppose that this unitary will flip it so that, let's just suppose it's basically the inverse. So f of 0 equals 1, f of 1 equals 0. So let's just assume that's what the function does. So then we have, right, so we have the top part, which is 0 plus 1. And then we have the bottom part, so we have 0 XORed with f of 1, 0 plus f of 1. I'm just writing this out. And then we have, actually just going to simplify this to 0 or f of x. I don't want to write it out. And then we have minus 1 or f of x. So we can clearly see that, okay, this 0 is just f of x, right? This is what it is, because 0 XOR anything is just whatever that other thing is. So if we're given this information, then we can see that, let's suppose we have, I'll rewrite this for clarity. Now we have this f of x, but we've just been told that in this case, we have two states, right? So we have the 0 state and the input state. So we have to sort of apply them, right? We say this is the inputs to this function, right? So we have writing it out. So if we continue this factorization, I just did it out already, with this f of x minus 1 XOR f of x, we get the following, right? We have this 0, and then it was 1 because f of x, remember what it does up here. We have 0, 0, 1, 1. Oh, sorry, it's a little typo. Oh, no, it's not. 1 x, or, yeah, that's a typo. Hold on. Yeah, there was just a brief typo, but I fixed it here. So we have 0, f of 0 is 1, 0, 1, x or f of 0. And f of 0 is 1, remember, so 1 x or 1 is 0, so we have this. Then we have 1 f of 1 is 0, 1 x or f of 1, which would be 1 x or 0, which is 1. So we get this. So now we can write this. So this is the state we have, reordering it. We can factor out a negative sign. Remember, global phases we can just disregard. So now we have this. We can factor this into this form, and we can see that this whole process resulted in what happened over here was, in this case, note that this is for a specific function, we got out of this negative, negative from plus negative and doing this controlled operation. So that's very interesting, important, and maybe counterintuitive. This will play a role in some algorithms. Let's also just briefly consider this sort of trivial example of if we have some unitary here that applies, once again, our operation. We can see the effect, right? And we'll show how to do this in code in a second. See the effect of what this is. And so suppose that we did this, right? So this is 0 plus 1. This is some effect here, 0 plus effect. I'll just put a 1. And so this is going to have some effect when we apply Hadamard to gate that will be measurable. So suppose we had some u over here that equals, right, when we do this, if we have this equation, right, we know that this is going to be an eigenvalue of this state, right? This is literally just the eigenvalue problem. So we can see that, I'm just making this more pretty, we can see that if we have this setup, right, this is a common thing we'll see in this format, then this is just a eigenvalue problem, and we can find the eigenvalue of a unitary operator by doing this, assuming it's doesn't change this, right? So if this was the z gate, this wouldn't necessarily work in the same way because the z gate on an arbitrary phi is not necessarily right. If we want to solve for here, this would be different, right? This has to be an eigenvector of z when this isn't necessarily an eigenvector of z. But if this is an eigenvector of u, then we can find the eigenvalues of u using this technique because it encodes this global phase down here into the local phase up here. So this is going to become important for algorithms in the future. But now let's look at the actual programmatic implementations. We can see that this is really quite simple code, and this actually is true for both of them. If you remember going over here, this example, what exactly is it doing? It's mapping 0 has no effect, 0 also has no effect, 1 flips the phase. And so this is clearly just a controlled Z operation. We're just writing it in a sort of different formalism. Anyway, getting back to the code, we can see, we have our basic circ operations. We make the 2 qubits. We do H, X on the second, H on the first, do our controlled operations. Now we collapse the superposition and measure. So if we actually do this measurement, we can see that we get a 1 on the first qubit, showing that it's changed, right? If we didn't have this CZ here, and we reran it, so I just got rid of the CZ there, right now it's 0, because we just controlled it. You'll notice you might suspect, well, hey, you're measuring both of them, there's some effect going on here. We can see that, no, even if I just measure one of them, it remains true that this, I'll even run it many times here. I'm running it 10 times. It'll be 1 for all of them. So that's the sort of principle of phase kickback. It's going to be important for a number of the algorithms that we will discuss in another video. But for now, that is all.